So this is exercise 5A, question number 1. A smooth sphere S is moving on a smooth horizontal plane with a speed u when it collides with a smooth fixed vertical wall. So the wall is smooth, the sphere is smooth, and is moving on a smooth horizontal plane. So we know that. So if you think about it, if I draw this in a 3D, you have a smooth sphere. It is moving on a smooth horizontal plane, and it is colliding with a smooth vertical wall. So my drawing is a bit untidy, but I hope you get the idea. So that's how it looks like. So that is what horizontal flow. So this is the horizontal flow, and that is the vertical wall that we are talking about. So now if we look at this from a bird's eye point of view, you would have your wall, and then you would have your ball that is kind of approaching the wall. So this is the vertical wall. So this is like a bird's eye view of things. And now let's see how to solve this. So I always like to draw it horizontally. So I would like to keep this like this, and the ball is kind of approaching the vertical wall this way. So I always like to draw it like that. Now it's completely fine if you would like to draw it this way as well. Whichever one you prefer, it's still gonna be the same. Right. At the instant of collision, the direction of motion S, it makes an angle alpha with the wall. So we know that this angle is alpha. This is before the collision, and I know that is the angle. It is moving with the speed u, so I know that this is u, and then because I know this much, I can then straight away write the vertical component is u sine alpha, and then the horizontal component is u cosine alpha. We also know that tan alpha is 3 over 4. So I know tan alpha is 3 over 4, which means if I make a little triangle here, this is alpha, tan is 3 over 4, so I know this is 5. Why does this useful? This would then be useful to figure out what is sine alpha and cosine alpha in the later part of the question. The coefficient of restitution between S and the wall is 1/3. So let's write that one down. We know that E is 1/3. Find the speed of S immediately after the collision. So what we're trying to find is, we are trying to find what is V, or the speed after the collision. So to find the speed after the collision, we will first have to find what is the vertical component, and we find what is the horizontal component, and then we could just go square root of x squared plus y squared. So first thing that we know, so let's, in the next part they're going to talk about the angle. So what we can do is, right, okay, before we go to the angle, let's just finish part A. So for part A, I know that u cos alpha is going to be the same throughout after the collision as well. So I can say, so first let's find what is u cosine alpha. U is u, cosine alpha, so tan alpha is 4, so cosine is adjacent side over hypotenuse, so that is u times 4 over 5. So I know this is 4 over 5 u. I have to find what is the vertical component. remember, vertical component will be affected by the coefficient of restitution. So this will be E times whatever is my initial one. So this will be E times U sine alpha. So what is U sine alpha? U sine alpha is 3 over 5. So this will be E times U sine alpha is 3 over 5. And then I know that E is 1/3, so I can say this is 1/3 times 3 over 5. So the vertical component would then be U over 5. So I've got my, so if I think about this as a vector question now, I know what is y, I know what is x. So my vector would then be square root x squared plus y squared. So I can then say the speed at which it is moving after the collision is square root u over 5 squared plus 4 over 5 squared. So that would then be, I can pull out the u, square root 1 over 25 plus 16 over 25. So that would be square root 17 over 25. So that's 0.823. So that is 0.823 times the original velocity. So that is the speed of s immediately after collision. Now, this is another keyword which I didn't kind of explain, the angle of deflection. So the angle of deflection is how much is the total angle that you have kind of changed or traveled through while your entire journey. So if you think about it, initially we made an angle alpha, then we made another angle, let's call this angle as beta. So this angle is beta. So the total angle that I have made, or that I have kind of changed my path, that would be equal to alpha plus beta, and that is called the angle of deflection. So I have initially made an angle alpha, then I changed my path again through an angle beta. So the total angle that I've entirely changed, that is alpha plus beta. So to find what is beta, always remember, you've got y, you've got x. So what we can do is tan of beta is y over x. So you have u over 5, you can divide that with 4 over 5u. Divide them, you've got 1/5 divide by, that's 1/5, divide that by 4/5, and that will be 0.25, and then we could do tan inverse of 0.25, that will be 14.03. So 14.03 is the angle at which I am leaving the wall. So we can go 0.25. So beta is equal to tan inverse 0.25, which is, kind of forgot, should have thought of that. Oops. Shift tan inverse 0.25, 14.03. And then the incoming, or my speed of, the angle of approach, that will be tan inverse 3 over 4. So inverse 3 over 4, that will be 36.8, 36.8 36.9. Well, let's just take that to be 36. So I can say alpha is equal to tan inverse 3 over 4. So I can take that to be 36. Now let's take this to be 14 degrees. So that's 3 significant figures. So the angle of deflection will be 36 plus 14. And then that should be equal to 50 degrees. So angle of deflection is your angle of approach plus your angle of separation. And yeah, that's pretty much it. So all we have to remember is horizontal component that just gets carried over from before the collision to after the collision never really changes. Whatever was my initial velocity, that is vertical, it just gets times by the coefficient of restitution.